In this section, we are going to study the linear first-order equations. In general, a linear first-order differential equations has the following forms. A sub 1 is a function of x times dy dx plus a sub 0 function of x times y equals g function of x. When the a sub 1 x is not equal to the 0, we obtain the standard form given by these equations. So this by dividing the a sub 1x dy dx plus a sub 0 over a sub 1 x y equal gx over a sub 0 x. So this part we change the px. At the right hand side is fx. When the coefficient of the derivative becomes 1, we call it is standard form. So we are going to consider these equations. To solve this first order differential equations, it's better to consider the integrating factors. Integrating factors plays a crucial role to solve a linear first-order differential equations. Integrating factor is calculated exponential power index integral px dx. Differential equation is transformed into the standard form given by dy dx plus px y equal fx. Using this px substitute into these equations, then we could find the integrating factors. Once we obtain the integrating factors, we multiply the integrating factors with the standard form of our first-order differential equations and combine two terms in the left-hand side into a single terms. So we multiply the integrating factor in the both sides of the equations. This is the integrating factors. So by comparing the standard form of the differential equations, you find out the integrating factor is multiplied in the both sides of the equation. Then you could consider the two terms in the left-hand side. So I'd like to show you that these two terms, exponential px dx dy dx plus px exponential px dx y. So these two terms is combined into the single terms equal d dx exponential px dx y. First one is a derivative of y and not derivative of the exponential functions. If you want to find the derivative of the exponential functions, it becomes exponential function times the derivative of the power index. So derivative of the power index becomes a p times y. Okay, then I showed that we could combine the two terms into the single terms. Then once we obtain these equations, d dx exponential px dx y equal fx exponential px dx. Then we could perform the integral in the both sides. Then left hand side becomes exponential px dx y equal, then we could find that y. Okay, this is how to solve the linear first order differential equations with integrating factors. This is a very standard method to solve the first order differential equation. The next section is a nonlinear first order differential equations. Sometimes it's quite difficult to solve the nonlinear first order differential equations, except some special case. This is one of the special cases. The following nonlinear differential equation is called the Bernoulli's equations. Left-hand side is exactly same with the standard form of linear first-order differential equations, but right-hand side is fx times y to the n. To solve the Bernoulli's equation, introduce a new variable of u. U is equal to the y to the 1 minus n. Then if you want to find the derivative of the u with respect to x, it becomes 1 minus n times y to the minus n dy dx. So from this equation, dy dx is expressed 1 over 1 minus n y to the n du dx. Then you can substitute into the differential equations. Then differential equations, it becomes 1 over 1 minus n y to the n du dx plus px y equal fx y to the n. We have a y to the n by dividing by y to the n. This equation is changes du dx plus 1 minus n px. This is the y to the 1 minus n. So this is u equal 1 minus n fx. So we obtained this equation for u. Actually, this equation is a linear first order differential equations for u. We can use integrating factors. Then we could solve these differential equations. So Bernoulli's equation is a nonlinear differential equations, but we could convert into the linear first order differential equations. We could solve the Bernoulli's equations using this method. Next equation is a nonlinear differential equation, but has a special forms. The following nonlinear differential equation, dy over dx equal f is a function of ax plus by plus c, but b is not equal to the 0, can be solved by the substitutions of the u equal ax plus by plus c. So we consider this is equal to the u. Then find the derivative of the u with respect to x. Then it becomes a capital A plus b dy dx. The derivative of the c with respect to x becomes 0 because the c is a constant value. So from these equations, dy dx is equal to 1 over capital B du dx minus a. Substitute back to the differential equations. Then differential equations becomes 1 over b du dx minus a equal fu. So du dx is expressed a plus b fu. This is separable equations. The right hand side is just only the function of u. So we use a method of the separation of variables. So du over a plus bfu equal dx. And integrate in the both sides of the equations, we could find the solution for u. Once you find the solution of u, you can find the solution of y. Okay, this is a method by the substitution to solve the nonlinear differential equations. Next section is the exact equations. A differential equation becomes an exact differential when it is expressed as a differential of a function. So we consider the m, capital M dx plus n, capital N dy. If this form of the equation happen to express the df, then from this equation you can easily integrate. fxy is constant because the derivative of the f becomes 0. So we could solve the differential equations. So we call that this form of the equation is the exact equations. The criterion for exact equations. Differential of a function is expressed is round f round x times dx plus round f round y dy. So this is equal to the exact equation for the m dx plus n dy. You can compare these two. M, capital M. This is capital N. M is round f round x. Capital N is round f round y. The second derivatives of the round square f round x round y is equal to the round y round x. So this from these equations, this is round x round f round y equals round y round f round x. Then you can substitute these expressions here. So this means round x. So this is n equal round y. This is m. So if we happen to find these relations, this is a necessary and sufficient conditions for exact equations. If you have an equation for the m dx plus n dy equals 0, then m and n related with these equations, this equation is expressed df equals 0. From this f is a constant, we could solve the differential equations. So we have to check if the m and n is related with this equation to solve the differential equations. Okay, this is another form of a first order differential equations. I explained how to solve first order differential equations.